Let's pick up where we left off. As a quick recap, let's remember that we talked about production and the production function, where the production function is simply the technical relationship between the inputs that are used and the output that's produced. We also talked about different types of inputs, namely land, labor, capital, and management. Inputs were further subdivided into those that might be fixed at some point in time and those that might be variable at the same point in time. The notion of fixed versus variable inputs also led to the idea of the short run versus the long run, where in the short run at least one input is fixed, while in the long run all inputs are variable. We talked about total physical product. This is simply the relationship between output and an input, and showed how total physical product can be used to determine average physical product, where average physical product is simply the level of output divided by the level of inputs that are used. This is different from marginal physical product, where marginal physical product measures the change in output arising from a 1 unit change in the input. Marginal physical product also led to the idea of diminishing marginal returns, where it's true that after some point of production, the amount of output that's produced by the addition of another unit of the input becomes smaller and smaller. That is to say, output increases at a decreasing rate. We can use the notion of average physical product and marginal physical product to actually characterize different stages of production. In a traditional sense, there are 3 different stages of production. In stage 1, average physical product is increasing and marginal physical product exceeds or is greater than the average physical product. What this means is each additional unit of input increases the productivity of the previous units of the inputs that are used. For example, as more nitrogen is applied to a corn crop, the output per unit input could increase. When that happens, we know that we're in stage 1. Another way of characterizing stage 1 is to say that output is increasing at an increasing rate. Stage 1 ends when average physical product is at its peak. It's also at this point where average physical product equals marginal physical product. This figure illustrates average physical product and marginal physical product, and the point where they cross is the point that demarks the boundary between stage 1 and stage 2. What we see is that in stage 1, marginal physical product, which is the green line, is above average physical product, and at the same time average physical product is increasing. One important consequence of stage 1 is that if it pays to use any of the input, it will pay to increase input use until the end of stage 1. It would be irrational to produce in stage 1 since you can get a larger average return, that is, average output, for each unit of input if you use more of it. The point being that if you're in stage 1, it will always pay to increase the amount of input that you're using so that you increase output beyond the level of stage 1. Stage 2 happens when average physical product of the input is decreasing and marginal physical product is below the average physical product. But, and this is important, but marginal physical product is still positive. Output is still increasing, but it's now increasing at a decreasing rate. What this means is that each additional unit of input decreases the productivity of the previously applied units of the inputs. Stage 2 ends at the input level where marginal physical product of the input is 0. This is the same graph that we showed before, and we can actually use it to illustrate the boundary between stage 2 and stage 3. That happens when marginal physical product crosses the axis, the 0 axis, as illustrated with that second black vertical line, and we can denote this as stage 2. So stage 2 is the region of input use between where average physical product and marginal physical product cross, and where marginal physical product becomes 0. Stage 3 begins at the peak of the total physical product curve. Input use beyond that point actually decreases output. When that happens, we know that marginal physical product is negative. The idea here is that it would be irrational to produce in stage 2 since you can get more output by using less of the input. An example of this might be the nitrogen being applied to corn example that we talked about a few minutes ago, where it doesn't make sense to apply increasing levels of nitrogen because at some point the application of that nitrogen will actually end up damaging the crop and reducing your yield. Stage 3 happens everywhere to the right of the boundary between stage 2 and stage 3. That is to say, everywhere where marginal physical product is negative. Now, we've talked about production quite a bit, and that discussion has focused on the relationship between output and a single input. That is to say, when all but one input is fixed. That's actually a fairly simplifying assumption. What we'd like to do is expand the discussion to allow for two variable inputs. For example, every business can alter the amount of labor and capital that's used in production. So we'd want to be able to capture that. However, the relationship between output and more than one unit of input is not easy to show. We can use the production function and some fairly complicated mathematics to characterize these relationships, but that's perhaps beyond the course. We can, however, depict the relationship between output and, let's say, two inputs graphically or with a figure as follows. Now, what I'm going to do is plot a figure from the textbook. And this is simply the production surface with two different inputs. So we're going to assume that capital and labor are our variable inputs and that we obtain a number of units of output given the amount of capital and labor that we're going to use. Now, when we look at this figure, it looks a little complicated, so let's stop and think about it for a minute. There's actually three axes that are being drawn. One axis that goes towards the east measures labor. That's the units of inputs, your labor input that you're using. Another axis that goes up to the north is capital. That's the other input that you're using. We're going to take different combinations of labor and capital to determine output. And output is measured vertically. That is to say, it's measured as the height of this production surface, where the different grid points on that production surface will indicate different levels of output. We can illustrate what would happen as we change the level of input use associated with one of these variable inputs. For instance, let's suppose that we have 24 units of capital being used but no labor. That would position us at point A on this production surface. As we increase the units of labor that's being used but hold capital fixed, we actually increase our level of output. So if we increased our level of labor to 18 units, we would move along the green line that's illustrated in the figure up to point B. And the height of point B tells us how much is produced. If we further increased labor to 24 units, we would then move to point C of the production surface, where again the height at point C tells us how much output is going to be produced. Now this figure is quite useful because it illustrates that we can have different levels of these inputs and still produce a constant amount of output. In fact, it's important to understand that this kind of a relationship is quite important in economics and that we can use this sort of figure to explore the trade-offs that would exist in the production process. For instance, one might be able to ask how much labor would be needed to keep output at a constant level while reducing the level of capital. To illustrate that idea, we're going to redraw that production surface, but with some different coloring and shading to try to illustrate an important principle. And what we want to do is emphasize that in these production surfaces, what we're keying in on are contours of the production surface. This is just that graph drawn again, but with different shading to illustrate different points. The solid lines that you see drawn around that production surface illustrate points where the level of output is constant. These are very much like contour lines on the topographical map, whereas we move further and further away from the origin and up the production surface, we're going to a higher and higher level of output. And again, we can think about what would happen as we vary one of the inputs. Let's suppose that we want to keep output fixed and that we're currently producing at point B. At point B, we have 18 units of capital and 6 units of labor. Let's suppose that when we're using 18 units of capital and 6 units of labor, we're producing 25 units of output. If we wanted to hold our our output constant at 25 units but reduce our amount of capital, how would we do that? Well, in this situation, the only way that could happen is if we use more labor. So if we wanted to keep output fixed at 25 units and reduce capital, we would move somewhere along the line that's denoted A, B, C, D, and E. So for instance, one option would be to reduce capital from point B to point D. When that happens, we would lower our capital level from 18 units to 6 units and increase our labor from 6 units to 18 units. That line is very important. In fact, all of those contour lines are very important in the context of economics because they reflect the trade-offs that must be borne in order to achieve some outcome. In this case, the trade-off is how much capital am I willing to give up in order to use more labor. I could go the other way and say how much labor would I want to give up in order to use more capital. The decision on how much capital and labor one would use to produce 25 units of output would obviously be driven by economics and would depend on both the price of the output and also, and importantly, on the cost of the inputs. The other important point to note from these contour surfaces is that they tell us something about how inputs can be substituted for one another. And in fact, they're so important in that sense that economists have given them a specific name. They're called isoquants. That comes from the Greek word iso, which means the same, and quant, which means quantity. So along one of these thick lines that you see, output is being held fixed, the quantity produced is being held fixed, it's constant, it's the same, hence we call it an isoquant. Now we can think about these isoquants in terms of a little more simplified diagram. So we're going to switch gears now and say, let's suppose instead of looking at this production surface, that we were hovering directly above the labor and the capital axis, looking squarely down on it. It's almost like you're looking down on the floor and someone has drawn the L axis and the K axis. And in fact, that's what we're going to do. We're going to talk about these isoquants. Now again, remember, an isoquant is a curve that shows the efficient combination of two inputs that can be produced at a given level of output. Now that's an important point, is that it's efficient. This is the most that we can get from those two inputs. What I'm going to do is draw a diagram where I have an X and a Y axis. The Y-axis is going to be the units of capital that I use in the production process. The L-axis is going to be the units, or sorry, the X-axis is going to be the units of labor that I use in the production process. If I were to hold output fixed at 100 units, say, and I were to draw an isoquant for it, it would look something like this. Note that it's downward sloping, and the points off the boundary, that is to the right of the isoquant, are inefficient. Now let's just suppose that I'm going to produce 100 units of output with different units, different levels of capital and labor. That level of output would increase as I move further to the right. The idea there is that you're moving from one contour line or isoquant on the production surface to a higher contour line or isoquant on that production surface that was shown in the previous graph. If I chose to produce 100 units and I was using, let's say, L1 units of labor and at K1 units of capital, and I'm off that isoquant, that is, I'm on that blue dot that's off to the right, that would be inefficient. The reason why it would be inefficient is that I could actually still produce 100 units of output, but use either less capital or less labor in different combinations. So for instance, I could produce 100 units of output with L1 units of labor and K2 units of capital. This is a good place for us to stop. We'll pick up the rest of this discussion with a review of these isoquants and then talk about how they're used to measure different relationships in the context of production.